This session will probably be fairly short. So let's take our automaton we've been talking quite a bit, M1, and find its language. So we want something in the form of this automaton's language is A. So we want a description of what A is. What's its function? What this automaton M1, what language does it recognize? Okay. So we want something of the form L of M1 is A, but what is A? Okay. So M1 is recognizing A, if you like. Well, for M1, the machine we've been talking about, this, I don't know if you can see it here, but, the three state automaton we've been talking about a lot. So here's a description of your language. Remember, a language by definition is just a set of accepted input strings. Okay. So here are your input strings W, such that now here's a description of what the properties that the input string has to have to be accepted. In other words, it's a description of the job, the function of your automaton. What's the automaton doing? What language does the automaton recognize? What properties do the strings of that language, the members of that set, what properties do they have to have? Well, here. Now, after doing some experiments, inputting various different strings to see which ones are accepted, which ones are rejected, eventually you come to some kind of conclusion, and here it is. So the accepted strings, W, they contain at least one, a single one, at least one, and an even number of zeros that follow the last one. Now you may say, "No, wait a minute. One, just with one symbol, goes through, and 0, 1 goes through, and 1, 1 goes through." Because we did that 2 sessions back. And they don't have any zeros at the end, but it's a bit of a trick. Well, 0 is an even number. Okay. So this. There's an AND here, so you have to have at least 1, 1 in the string, and after your last one, you need to have an even number of zeros. Okay? Now that even number could be 0 zeros. No zeros after the 1. So another way of saying that is, well, your last symbol is 1. So it's okay, so it's consistent, it's not contradictory. Alright? Okay, now, so double lines, that usually means sort of major new topic. Well, it's not really, but we're now going to start doing some examples of finite automata besides M1. We'll do quite a few of them. And each time we will use the formal definition. We'll write out that each automaton's formal definition. We'll write out its 5 tuple. Okay, the Q, the sigma, the delta, the Q0, and the F. Okay, and we'll specify what those 5 things are for that given automaton. Right? Okay, so here's a state diagram, state transition diagram for a machine M2. Right, so that's our next one. Now, it's a bit simpler. We only have 2 states now, not 3. Before we had 3. Now we've only got 2. And the start state, obviously, here's your disconnected arrow. So that's pointing at the start state. So we know the start state's Q1. We have one accept state. That's Q2. Okay, and we have all these transitions. So okay, let's let's give its formal description using the formal definition. So M2 will be, now here's your capital Q, it's just the list of states, it's just Q1, Q2, that's obvious, right? The set of states, so Q1, Q2 as a set of members. This is sigma, that's the alphabet. The set of allowed input symbols, right? 0 and 1, so that's just the binary alphabet. Delta we'll do it separately because it's a whole table, right? And the start state is Q1, so we've got Q1 here. And the set of accept states, well, there's only one, so there'll be wiggly brackets Q2. The set was just one member, this state Q2. Alright, now the transition function, the delta, we can write out in the form of a state transition table. Now, well, there's only 4 entries, so let's actually do it completely. We've not done this before, but let's do it. Okay. So for each state and for each possible input symbol, we need one next state. Okay. Now we have 2 states and 2 input symbols, so that's 2 by 2. We're going to have a table with 4 entries. So let's do it systematically. So Q1 naught, and then we'll do Q1 1, and then we'll do Q2 naught and Q2 1. Okay. So from this state diagram or state transition diagram, let's calculate what the next state is in the 4 cases. Okay. So Q1 naught. Q1 naught will take you back to Q1. So Q1 naught gives you Q1. That's correct. Okay, now Q1 1. So Q1 1 takes you to Q2. Q1 1 takes you to Q2. So that's correct. Okay, now Q2 naught takes you to Q1. Q2 naught takes you to Q1. And Q2 1 takes you to Q2. Q2 1 takes you to Q2. Alright, so that's your transition table, state transition table format to describe your transition function. Right? You're describing the transition function in terms of a table, a state transition table. All right, so that's your delta. The start state's Q1. It's pretty obvious, and the set of accept states, well, there's only one, so that's the set with one member, Q2. Okay, so that's fairly obvious. Okay, now note here from the text, the state diagram and the formal description, this, with this, there's your formal description, and the state diagram, they are equivalent. You can go from one to the other. From the state diagram, we created this formal description. Right? So we can go from this to this, but we go the other way. Right? We could from this description we could draw a state diagram or state transition diagram. Okay, so it can go either way. They're equivalent. They're just different ways of writing the same amount of information. Okay, they're equivalent. All right. Now, okay, so you're given this formal description, or